Good afternoon, students. Welcome to the live lecture of functional analysis. In the last lecture, we have seen the definition of subspace of a normed linear space. Actually, we are familiar with subspace of a vector space earlier, right? What is subspace of a vector space? The given set should be a subset and a vector set, a vector space itself. Likewise, here also one can say that subspace of a non-linear space can be defined as first it should be a subspace of a given linear space, and secondly the norm values of the elements in the subset is same as the norm value of the element considered as an element of the given space, right? That is norm y of t is equal to norm of t for all t in y. In this case, one can say that norm value of both norm value of an element of y is same for both the norms. Norm defined on x, norm defined on y. With this definition, one can say that this norm y is a restriction of norm function, or norm y is a norm induced by this norm defined on norm x. Okay. With the help of this definition, we have seen two important theorems. First is every complete subspace of a nonlinear space is closed. In order to prove this closed, we have to prove that it contains all its limit point, and that we have done. Okay. And the converse need not be true, that is the one part, and the converse is true if the corresponding space is the Banach space. Therefore, here we have proved the next one as every closed subspace of a Banach space is complete. Okay. Then later we have moved towards the quotient norm spaces. Before that, we have seen what is the quotient space actually. This word quotienting, this word quotient comes because whatever this quotient group or ring or space we were considering, this is going to give us the partitioning or quotienting of the corresponding set. Right? This is what a simple example I have taken in order to show you. Then in order to find the quotient space, one has to start with an equivalence relation, and the equivalence relation defined on the linear space X is of this type. X1 is equivalent to X2 mod M if X1 minus X2 is in M is the condition we have defined. We have verified one by one that it satisfies reflexive, symmetric and transitive property, so that it becomes an equivalence relation. And with this equivalence relation, this corresponding vector space or the linear space is being partitioned like this into the small groups, small equivalence classes. Why it is being partitioned? Due to this property of the equivalence classes. If A, B are the two elements of X, then the equivalence class is either disjoint or exactly same. Then we have seen that the set X by M, the quotient space we have defined, is actually the collection of all cosets of the type X plus M for all X in X. This we can write as an equivalence class also. Here I have shown you how that equivalence class becomes the coset. Right? Then we have we know that this X by M becomes the linear space under the two operations of addition and scalar multiplication. If you want to verify, you can verify all these 10 properties of the linear space or the vector space by taking these two operations, addition and scalar multiplication. That of the zero element of this corresponding space is the set M itself, right? This is what a quotient space. Then we are coming towards an important theorem proving that this quotient space is the quotient norm space, right? Then the norm on this quotient space is defined like this. The symbol used is norm 1. The symbol used is norm 1. What is the meaning actually? The symbol used for the norm on X is simply this norm. That of the symbol for norm used on this quotient space is norm 1. Okay. In some book it was used with norm dash also, just to make it different from this norm defined on X, right? Norm 1, norm dash, norm star, anything one can take. Therefore, what is norm 1 defined? Norm 1 of X by M, because the nature of element in this set X by M, a quotient space is a coset, right? Now, coset of M. Therefore, this is of the type norm 1 of X plus M is defined to be inferior norm of X plus M for all M in M. Now then we wanted to prove that This norm 1 is a norm on x by m, and if x is provided to be Banach space, then this norm quotient norm space is also the Banach space. This is what visualization. X by m, if I write, this will be the equivalence classes or the partitions. Okay, now for any x in x, if m is the set, this x plus m is actually a shift, no? Right now, as of we were doing on the real line, correct now, translation or a shift one can see. On the parallel lines here also x is added to every element of m. Therefore this set m is shifted to a new position like this. Correct now? This m is shifted to the new position like this. Then what we wanted to do, x plus m, we were x plus m be the nature of element of x plus small m will be the nature of element of this set x plus capital M. Then we will join all those elements with the origin, right? We will join all the elements with the origin and we will find out the norm of every element of this set x plus m, right? Norm of every element. Now which norm is acting now? If x is in x, sorry, if x is in x, okay, m is an element of capital M, where m is a subset of x, then what about this x plus m together, where it is going to be? This is going to be a member of a capital X, no? Yes or no?
Yes, ma'am.
Yes, ma'am.
For m in m is a subset of x, therefore x plus m is going to be in x. And we know what is the norm acting on this set x? Simple norm, right? Therefore we will find out the norm of every element and whichever will give us the inferior one. Whichever will give the inferior, right now will be the norm of the corresponding set. It is of the type, right now. Why we were finding inferior not superior? Can anyone guess? Yes, can anyone guess why inferior not superior? Whichever the smallest we were counting, the largest one we were not counting. Okay, just to make the uniqueness. Just to make the uniqueness, we were taking the inferior among all the calculated distances. One can check for the superior as well, right? Now, what is the job to prove in this today's lecture? This norm 1 is a norm, verifying 4 conditions. Then, assuming x is a Banach space, we have to prove that this quotient space is also Banach space. Norm we have already verified, therefore it remains to show the completeness property only. Okay, let us proceed in today's lecture to prove this is a norm. Here I will just rewrite the definition of norm 1. Norm 1 of the set x plus m is defined to be inferior norm of x plus m on the condition m is in m. This is the norm defined. Okay. Let me tell you again, this is the norm defined on x is with us, and this we wanted to prove to be a norm defined on x by m. Okay. Shall I proceed for the proof now?
Yes, ma'am.
Yes, ma'am.
Okay, step 1, we will first prove that this norm 1 is a norm on x by m. Let us verify all the 4 conditions one by one. What is the first condition to prove?
Non-negative.
Yes, non-negative. Norm 1 of x plus m is non-negative we wanted to prove. But if you look at this definition, norm 1, this is inferior of norm x plus m. Now this x plus m is always non-negative, no? Every x plus m. Therefore, what about the inferior one? If every element of the set is non-negative greater or equal by 0, can I say the inferior is also non-negative?
Yes, ma'am.
Yes, ma'am.
Therefore, here I just write norm 1 of x plus m is inferior norm of x plus m provided m is in m. Now here I will write directly norm 1 of x plus m is non-negative. And what is the reason I am giving here? Since norm of x plus m is non-negative for all m in m. Okay? What is the second to prove?
Norm x equal to 0 implies x equal to 0.
Very good. Now we will write for our set. Norm 1 of x plus m is equal to 0 implies and implied by, yes, x plus m is equal to,
M.
yes, it is m. Why m? Because this m is 0
0
element
element.
of the quotient space, right? Now we will assume one part. Okay, then we will prove the reverse. First I will assume norm 1 of x plus m is equal to 0. Okay, according to the definition, this gives me inferior norm of x plus m provided m is in m is equal to 0, right? Now what is inferior norm x plus m is equal to 0? Every term is non-negative, but we were saying inferior is equal to 0. Means, can I say there are some elements whose norm is tending towards 0?
Yes, ma'am.
Okay, here this is the set, say x plus m I am writing. Okay, if 0 is the element of this x plus m, then it is okay. Otherwise, we have to go for, these are the elements, no? Which type of element these are? X plus m1, x plus m2, and continue somewhere here it is x plus mn and so on. Calculating norm of x plus m1, if 0 of your vector space x, if is in the same set, then it is okay, as of I shown you here. Assuming 0 is in the same set. But sometimes the 0 may or may not be of the same in the coset. If 0 is outside, okay, 0 is outside, one can check it on the outside. Then to find out norm 1 of x plus m, what we have to do? We have to join this x plus m with 0, this x plus m2 with 0, x plus m3 with 0, like this, right now? Then whichever is giving us, we were assuming that inferior is 0. Means there are few elements, I can say at the boundary, na, here. Those are converging to 0. Therefore, just let me rewrite this as there are few elements x plus mn. Not all is giving us 0 value, right? Therefore, few elements we were guessing which are giving us the inferior value to be 0. Okay. Why I have written mn instead of m? Just to identify those elements which is giving me the norm value to be tending towards 0, so that my inferior can go to 0. Therefore, if inferior of this set is equal to 0, can I write? See, can I write? This implies as norm of x plus m is equals to 0 for all inferior terms. For all inferior terms, may I write norm of x plus mn is tending to 0, and I will write this as n tends to infinity. We have identified those elements whose norm is tending towards 0. Therefore, we get one sequence actually. What kind of sequence here? Let me just rewrite this term as mn minus of minus x. Is that okay?
Yes, ma'am.
So here can I collect a sequence of elements in M such that this mn sequence is converging to minus x. Right now? Okay. Therefore, can I write? There exists a sequence Mn in which set the sequence will be in x or m. In which set the sequence will be?
M.
Yes, it is in m. Such that, what such that? Norm of x plus mn tends to 0 as n tends to infinity. Okay. That is, can I write limit n tends to infinity, mn is equal to minus x. But what this x is gives me then? May I say x is the limit point of the set m?
Yes, ma'am.
But what kind of set m is given to us? Closed, right? Closed subspace m of x. Let me just check statement. What is m given to be? Cn. M be a closed subspace, right? Now if it is closed, where this x belongs to? Minus
And
x I can do. Minus x and then again x it will be, no? Minus x is the limit point I will. Therefore I cannot write minus x is in m. Right? Can I write x is in m? Because x will be additive
yes,
inverse of
ma'am.
minus x, right? No. Therefore, if x is in m, what is the nature of x plus capital M?
It is also in M. Capital M.
Yes, it is capital M, right now? Therefore, we have proved one part. Norm 1 equal to 0, we have proved x plus m is equal to m. Now, let us think conversely. Conversely, what to assume? X plus m is equal to m. Okay, and we wanted to prove the norm 1 is 0. Therefore, let me consider norm 1 of x plus m. As per the definition, this is inferior norm of x plus m provided m is in m. And where is this x? Okay, if x plus m is m, okay, x plus m, where this x plus m goes? Or can I write here
Yes.
only? Can I write over here only x is in m? X plus m is m, it implies x is in m. Is that okay? Right now?
Yes, ma'am.
Or I can make implies and implied by here. Right? X plus m is equal to m. It happens only if x is in m. Right? Now think of, I will just add point here only so that it will be easier for you. Can I write x in m here only? Now m is in m, x is in m. What about x plus m? It is
It
in
is
m
in M.
again. Okay. Therefore, this is actually inferior of an element of the type y. Y is in m. Clear? Okay. This is an element of m again, no? Therefore, instead of writing element of m like this, I'll write norm y such that y is in m. What is the inferior value? M is a subspace. Rather closed, no? Closed subspace. Can you think what is the inferior value of the norm?
0.
0. Why? Why? Yes, you're correct. Why 0? Why 0 belongs to m?
Non-space n by x by m is m itself. That's why it is equals to 0, na?
No, no. Actually, m is a subspace. Therefore, it contains additive identity 0. Right? Na?
Yes, ma'am.
Ah,
Yes, ma'am.
okay, with this reason. If m is a subspace, here can I write 0 is in m and all the
Yes,
rest
ma'am.
elements are
Yes, ma'am.
non-zero. If all the rest elements are non-zero, what is the inferior value I'll get? Non-zero.
0.
Non-zero is 0. Here, therefore, can I write this inferior value is 0 itself? Therefore, norm 1 of x plus m is 0. Yes, any difficulty?
No, ma'am.
Good.
No, ma'am.
Now, let me go for proving the third condition, triangular inequality. Right now? What to prove? Norm 1 of, I'll take two elements, x plus m and y plus m. These are the two cosets. Okay. And we wanted to prove this is less equal by norm 1 of x plus m added with norm 1 of y plus m. Okay, let me consider the left hand side. Norm 1 of x plus m added with y plus m. Okay, according to the definition of the addition defined in the quotient spaces, can I write this as x plus y plus m?
Yes, ma'am.
Next, now I'll use the definition. What the definition says? Inferior, okay, inferior x plus y I'll take as it is added with small m on the condition small m is in capital M. Correct? Now see what we wanted to adjust on the right side. We wanted to separate norm 1 of x plus m and norm 1 of y plus m. Means anyhow I wanted to separate these inferior values. Just to make the separation, I will write this element m as addition of two different elements of the capital M set. For the sake of convenience, for the sake of proving the result right. For this x plus I will keep as it is. And can I write this say m as m1 plus m2? Right? Provided both m1 m2 are in m again. Okay. Now let me separate. How I am going to separate? Check. This is inferior. Let me take x together with m1 and I will take y together with m2 with the same condition. Okay. Now I have to separate these two. I have to separate these two. How can I separate? Knowing this norm is a norm on x. Can we use triangular equality?
Yes, ma'am.
Therefore, can I write this is inferior less than or equals to inferior norm 1 of x plus m1, right? Added with norm 1 of y plus m2 provided with the same condition. Now I wanted to separate inferior also. Inferior of addition of two elements. What about the, if I want to separate, what kind of effect will be there? It is of this type, na? Inferior s plus t, two sets. And I wanted to write inferior s plus inferior t. What is the relation here?
Less equal, ma'am.
Yes, it is less equal. Therefore, this less equal continued as it is, and I will write this as inferior. First set I will collect norm of x plus m1. Now I will write simply m1 is in m. Okay. Then added with inferior norm y plus m2, and here I will write m2 is in m. Now if we look at the condition, okay, if I look at the two statements, what kind of norm first statement is?
Norm 1 of x plus m1.
Good. This is less equal to norm 1 of, is it x plus m1 or x plus capital M?
X plus capital M.
Yes, it is capital M. Okay. Hence we have proved the triangular inequality. Now lastly we will go for separating the scalar, right? Now alpha is a scalar. I am using norm 1 of alpha times x plus m. We wanted to prove norm mod alpha into norm 1 of x plus m. This is easier, right? Now norm of alpha times norm 1 of alpha times x plus m. According to the definition, this is inferior norm of alpha times x plus small m added with such that m is in m. Okay, now this is the norm acting on x. So can I use a fourth property? May I write this as mod alpha into norm of x plus m. Right now?
Yes, ma'am.
Now the inferior this inferior is running over the elements of m. It is independent of alpha. Therefore, can I write take this alpha out? Mod alpha into inferior norm of x plus m provided m is in M. Okay, therefore what is this definition? Norm 1 of x plus capital M. Hence the proof. Okay, thus we have verified all the four conditions. Therefore, this norm 1 is a norm on the quotient space. Thus, all four conditions are verified of norm I. All four conditions of norm are verified or satisfied. Therefore, here I will write this norm 1 is a norm on the quotient space x by m. If this is a norm on x by m, what about this pair x by m with norm 1? This is a normed linear space. Normed linear space or quotient norm space. Okay. Now an important condition, an important step to prove that. What to prove? If X is Banach space, then x by m together with norm 1 is Banach space. Right now? Quotient norm space we have verified already. Non-linear space we have verified. What remains to prove then? Completeness only, na?
Yes, ma'am.
Therefore, I will write that is to prove that x by m is complete. Okay. Now to prove this to be complete, what one has to claim? We have to show that every Cauchy sequence is convergent. Okay. What will be the elements of the Cauchy sequence of x by m? What kind of nature it will have? Can anyone tell me? Nature of element of the sequence in x by m. Are the elements functions, sets, matrices? What it is? Or scalars? What kind of nature the elements will have? X by m. Elements in x by m. अशा प्रकारचे एलिमेंट्स. Yes, these are
x1
the
plus m,
sets.
x2 plus m.
Very good. These are the cosets of m rather, right now. Now to
Yes, ma'am.
prove the Cauchy sequence is convergent, can you just think it is a sequence of sets and we wanted to prove Cauchy sequence is convergent. Therefore, proving actually is a little bit difficult job. Therefore, to prove the Cauchy sequence convergent, what we will do, you might have knowing one of the result. The sequence is convergent if it has a convergent subsequence. Right?
Yes, ma'am.
Okay. Therefore, to prove a Cauchy sequence in this x by m is convergent, what we will do simply, we will extract one convergent subsequence. We will extract one convergent subsequence in the Cauchy sequence of x by m. Okay? Okay? Let me do that. Now here I will write let Sn plus m be a Cauchy sequence in x by m provided Sn is in x. Right? Now here I will write in the red pen. To prove, our job is to prove Sn plus m is convergent, na? Convergent or converges to a point in x by m. Okay, it is enough. I can write. It is enough to prove the sequence has convergent subsequence. Therefore, what we will do? We will construct or we will extract a convergent subsequence from the sequence Sn plus m. Here we will write. We extract a convergent subsequence from this. What's a sequence? As follows. See, the method is very easy, but you have to pay a careful attention. Okay, and you have to recall this twice and thrice. Okay, the sequence is Cauchy. What does it mean? Since the sequence Sn plus m is Cauchy sequence. Cauchy sequence. What is the definition? For every epsilon greater than 0, there exist two elements m and n.
Such that norm of Sn minus Xn less than epsilon.
Yes, norm of Sn minus m. But here, what is the nature of every element in Sn plus m? This is Sn1 plus m, Sn2 plus m, right now?
Yes, ma'am.
Here shall I write? What is the nature of element? Sn1 plus m, Sn2 plus m, Sn3 plus m. Every element is coset. Don't forget. Every element is a coset. Since Sn plus m is Cauchy, now what we were doing? We will put some particular values of epsilon and we were going to extract a subsequence from this, right? Okay, if you see what I'm writing, just see carefully. Since Sn plus m is the Cauchy sequence, given epsilon equal to half, we can find a positive integer n1 such that, what such that? Norm 1. Okay, what is the norm acting on x by m? It's norm 1. But here I will write Sn plus m, norm 1 of Sn plus n minus Sm plus m. Norm 1 I am writing, okay? Norm 1, this is less than by half and is true for all m n greater equal by n1. Is the definition clear? For this value of epsilon as half, we have got one stage after which this statement is true. Okay. Now I am going to consider this first element Sn1 as x1 and let me call it as statement number 1. Okay. Let me show you here. Suppose this is your first element, Sn1. Or I'll write 1, 2, 3. Okay, 1, 2, 3, and so on. Okay. What it was said that there exists a stage n1. What is the stage? Here it is n1. What is the element here? Sn1. Okay, here we will change the symbol for this. Okay. What is the first element we were writing now? Sn1. This is the stage after which, getting me now? This is the stage n1 after which this statement number 1 is true. Okay. And whatever is this first element we were getting, let me call it as x1. Okay. And this we have obtained for epsilon is equal to half. Let me just proceed further to just increase the value of epsilon again. Therefore, again we will increase the value. Given epsilon is equal to 1 by 2 square, we can find a positive integer n2 greater than n1 such that, this is the selection we were making. What such that? Again same statement, Sn plus m minus Sm plus m norm 1 is less than 1 by 2 bracket square and is true for all m n greater equal by n2, right? Let me call this as statement number 2. Okay, is that okay? And here,
Yes, ma'am. Yes, ma'am.
what I'm saying then again, let Sn2 is x2. Okay, Sn2 is x2 means the position we have obtained here. Next position, n2 is the next positive integer we have obtained, where it satisfies the inequality less than 1 by 2 square. Therefore, I'm going to call it as Sn2, which is equal to x2. See here, n2 is greater than n1 we have written. Okay, likewise, just go on increasing the values of epsilon. Sorry, go on decreasing the values of epsilon. Right now, here for this n1 epsilon value is half. Here it is 1 by 2 square. Let me make it 1 by 2 cube. What will be a next stage then? N3. And what is the position? Sn3. Let me call it as x3. Right? Means out of all Sn's, we were selecting some elements x1, x2, x3 so that it will form a subsequence of this original sequence. Right now? Subsequence of the original sequence. Is that idea clear up to this?
Yes, ma'am.
Okay. Now here I will just write then x1, x2 will satisfy. What it is going to satisfy? See, check. N2 is greater than N1. Therefore, here can I write the value? It is true for all mn greater than or equals to N1. Therefore, let me put the value of m as N1. Let me put the value of m as N1. Then N2 is greater than N1. Therefore, here let me put it as N2. Okay. Therefore, from this equation number 1, can I write Sn2 plus m minus Sn1 plus m is less than half? Sn2 plus m minus Sn1 plus m less than half, norm 1, no doubt. समजते का बघा हे? For all the values greater than n1 it is true. Which two values I have selected? Sn2 and Sn1. For all the values of the integers greater than n1, this equation 1 is true. For which values I have selected? One value I have kept m is equal to n1, then n I have taken n2. For equation number 1 is true for this values, right? But what is Sn2 and Sn1 we have fixed out? Sn2 is x2 and here it is x1. Therefore, this is norm 1 of x2 plus m, x1 plus m less than half. Let me call it as statement number 3. Okay. See, now as of we have selected n1, n2 and continuing this process. Okay. Up to which step I can continue? I can continue let up to nk, a stage nk. What is the corresponding element here? Snk. What I am going to call it as xk. And what will be the value of epsilon at this stage?
1/2 raised to k.
Raised to k.
1/2 raised to k. Good. Okay. So let us just continue the process and identify the elements x1, x2, x3 and xk. Therefore, may I say this will form a subsequence of the original sequence. Xn plus m, xk plus m, anything one can write. Okay. Here let me just continue. Having chosen n1, n2, dot, 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 nk and x1, x2, dot, dot, xk, we can find nk plus 1 greater than nk, right now? Such that, what such that? Norm of Sn plus m minus Sm plus m less than 1 by 2 raised to k plus 1. 1 by 2 raised to k plus 1 for all m greater or equal by nk plus 1. For k plus 1 I am going to write it. Okay. Let me call it as statement number 4. Then what is my position? Snk plus 1. Yes,
Xk plus 1.
Yes, it is xk plus 1. And then we will write it is a subsequence. Hence, we have obtained subsequence, whether it is a subsequence or not.
Yes, ma'am.
Subsequence, say
Yes.
xk plus m of what? Sn plus m. Because why it is a subsequence? We have not chosen all the elements which are present over here. We have selected few elements. We were not selecting the middle also. Few elements with the strategy we were selecting. Okay, whether we have changed the order, we have not changed, we have not disturbed the order as well. Therefore, whatever is the xk plus I am writing will be a subsequence of Sn plus m, such that, what such that? Norm of xk plus 1 plus m minus xk plus m. This value is less than norm 1. From this, can you tell me a value? X2 plus m minus x1 plus m is less than half. Then what for xk plus 1m plus minus xk plus m? Is it
1/2
One half
raised
raised to k plus 1.
k plus 1 or k? Check.
k.
K.
K it is, no. Here we have to count the order, degree.
Yes, ma'am.
Therefore it is k, not k plus 1, right? And for k equal to 1, 2 and so on. Let me call it as statement number 5. Okay. We have found a subsequence. Now what is the job? To show that this subsequence is convergent. Right now? Now we prove this subsequence converges to an element of x by m. But again, though we have found a subsequence, again every element of this sequence is a set. Therefore, to find the convergence, it will be easier for me to switch from sets to some points. Therefore, what we will do, we will select one element of every set of the sequence. What I am going to do now. Let's see what I am going to do. Initially, we have a sequence of this type, Sn plus m. Okay, where the nature of elements is, or I can write every element is set. Or set. Every element of this sequence is a set. Okay. Then later we have extracted a subsequence xk plus m. But again, may I say every element of this sequence is a set. Therefore, proving convergence will be difficult if the sequence is with elements as sets. Right? Therefore, what we will do, we will select one element from every set. What kind of elements we will have? Say x1 plus m is the first set, x2 plus m is the second set, x3 plus m is the third set, and continue. Somewhere xk plus m is my kth set and continue. Now what the job we will do, we will take one element of this set, say y1. One element of one element of this set, say y2. One element y3 and so on up to say yk. And we will form a sequence. Right? We will form a sequence. Okay. Then whatever the sequence will be formed, say yn, is a sequence of elements now, right now?
Yes, ma'am.
Now it will be easier for me to show this is convergent. Okay. Now what we will do, first we will show whatever this sequence yn we have selected is Cauchy. Okay, we will prove this is Cauchy, but this is a sequence of elements in X, no? This x1, x2, xn,
Yes, ma'am.
all these are the elements in X. But X we know it is complete. Therefore, once I prove that yn is Cauchy, it will converge to some element y in X. Right now? Then what remains to show simply, finally we will claim whatever is the original sequence xn will converge to y plus n. This remains to show. Understood the theme?
Yes, ma'am.
Initially we have sequence of sets, then we have taken it as a subsequence. From the subsequence, now we were extracting a sequence of elements, not sets, so that proving convergence will be easier, right? Now let me continue my proof. Our aim is to show that this sequence is convergent. Now what I will do, I will start with the first element. Let y1 I will select from the first set x1 plus m. Clear? Like this I have written y1 I wanted to select. Y1 I have selected. Okay. Then may I write the nature of element y1 is of the type x1 plus m1 for some m1 in m. Nature of element y1 is x1 plus m from some y1 in m1 in m. Now let me use equation number 3 to write. What is equation number 3? Check. Norm x2 plus m, x1 plus m is less than half. This I am using. Okay. What is this equation? Let me write. Norm 1 now. x2 plus m minus x1 plus m less than half. Correct now? Can I write it as norm of x2 minus x1 plus m? Norm 1. Okay. Okay. I wanted to write it as x1 minus x2. Therefore, what I have to do? I have to take minus 1 common. Na? But earlier we have proved that this norm 1 is a norm. Then how can I take this scalar out? With modulus, na? Modulus minus 1. Less than half. Okay. Therefore, we got this norm of x1 minus x2 less than half. What is the definition? This is plus 1, no doubt. Let me write the definition. What is the definition? Inferior x1 minus x2 plus m or m in m, and we wanted to show that this is less than this is less than half. This is the definition I have used, right? No? Norm 1 definition I have used. Here I can write by definition of norm 1. Correct? Inferior value less than half we know. Now let me claim inferior exists for some special value of, or for some special element of the set M. Hence there exist elements say M not in M such that. What such that? Norm of x1 minus x2 plus m naught less than half. That is inferior holds for m naught I am claiming. Okay. Now let me make an adjustment again. One element of x1 plus m y1 I have selected. Now the job is to select the another element from x2 plus m1. For to selecting the element, I will just want to separate this with adjustment, addition and subtracting the element m1. See how I am adding. x1 plus m1 I am writing. Okay. Then I am writing minus x2 minus m0 plus m1. Is it okay? Just plus m1 minus m1 addition. Why I am doing this? Because I know this is y1. Okay. This is y1. And x2 plus something. x2 plus some element of m. Can I write it as y2? x2 plus some element of m.
Yes,
Right?
ma'am.
Here I can write plus m1 minus m2. Therefore, this is an element of m. x2 plus some element of m. I will write this as y2. Therefore, here what I will choose? I will choose y2 as what? x2 minus m0 plus m1. So that we get what we will get. May I write? This is y1 and this is y2, which is less than half. Okay. Now let us proceed in the same manner. What I have to do then next? As of y, here from starting with an element of y1, we have selected y2 with equation number 3. Now we'll start with y2 We will select y3 from next equation. Here, what is my next equation in terms of x2, x1 if I write? This is x2 plus m like, sorry, x2 no. x3 plus m minus x2 plus m less than 1 by 2 square. Okay, we were not writing in that detail. I just said continuing in the same manner. We get what we get. Choose y3 in what? x3 plus m such that what such that y2 minus y3 less than 1 by 2 square. And again continuing, we can obtain a sequence yn in x such that what such that, can anyone tell me? Norm of yn
Right.
minus yn plus 1 less than what should be here? Half raised to
N.
N.
yes, it is n. Okay. Okay, now this is a sequence of elements. Now we have like this, which I told you. Selecting one element from every set, we will get y2 as a sequence of elements, not sets. Okay, now we will show that this is Cauchy. Okay, now we show that sequence yn is Cauchy in x. Consider norm of ym minus yn. Okay, here I am considering n greater than m. Just a case. Therefore, can I write this as ym minus ym plus 1 minus, plus ym plus 1 minus. I am making an adjustment, right? I think you are familiar with this kind of addition, this kind of adjustment. Right now, I have added just all middle terms. Then let me use triangular inequality to separate. What about every inequality? Number I have not written, na? This one. What is my number? Last number? 5 I have given. What should I give to this? Is it 6?
Yes.
Next. Now here I will just continue separating. This is yn minus 1 minus yn. Okay. If the first term is less than by what? This first. Check.
Half
Yn
raised to
minus
m.
half raised to m.
M.
Good. 1 upon 2 raised to m. This is 1 upon 2 raised to m plus 1. So on. 1 upon 2 raised to n. Is it n?
N minus 1. N minus
Yes,
1.
n minus 1. Good. N minus 1. What kind of series is this? Geometric progression, no?
Yes, ma'am. Yes, ma'am.
Geometric progression. First term is 1 upon 2 raised to m. Common ratio
1 half.
less than 1, na? Less than 1. Then what is the series sum? Formula?
A into 1 minus r upon 1 minus r raised to n.
Ulta you are telling me. A into 1 minus r raised to n upon 1 minus r.
Yes, ma'am.
But for less than 1, is it a upon 1 minus r only? For r less than 1. Correct, na? Let me just substitute the values. This is 1 upon 2 raised to m minus 1 minus 1 by 2. Right, no? 1 minus 1 by 2 is 1 by 2. Therefore, this is 1 by 2 raised to m upon 1 by 2. Therefore, 1 power will be decreased. Therefore, is it 1 upon 2 raised to m minus 1? Okay? Can I write directly in this statement? Thus, norm of ym minus yn less than 1 upon 2 raised to m minus 1. Therefore, may I say as m n tends to infinity, this will tend to 0.
Yes, ma'am.
The sequence yn is Cauchy sequence in X. Since X is complete, or since X is Banach space, hence it is complete. Hence it is complete. Therefore, may I say thus there exists a vector y in X such that, what such that? Sequence yn converges to y as n tends to infinity. Okay? Therefore, the sequence yn converges to y. Now, what is the aim to show? Here I have written, na? Sequence yn converges to y. But this yn we have taken one element of every point of this sequence. What is my next job to show? Xn plus m converges to y plus m. Last step of the proof. Okay? Now here I'll just make a separate para to conclude the proof. We show that xn plus m converges to y plus m in x by m. Okay, how can I show this is convergent? Both are the elements in x by m. In x by m nor 1 is working. Therefore, I will take a subtraction of this nor, these two elements, and I will either show this is less than by its law or it will tend to 0. Okay? Consider norm 1 now. Xn plus m minus y plus m. Okay? Now, can I write first this as xn minus y plus m in order to use the definition. Now, what definition says? This is inferior. Inferior nor xn minus y added with small m provided small m is in capital M. Right now? Now, I want the relation between inferior of all the elements and an arbitrary element. This is an arbitrary element of this set, no? Plus m1 plus m2, all these elements. And this is inferior. What is the relation between S is the set? Okay, then inferior S and any arbitrary element X. What is the relation here?
Less is equal.
Yes, it is less equal. So can I write here less equal? Okay. What is the left hand side? You are knowing. Norm 1 of X. Okay. Now what this I can write again. Let me just rewrite this as norm of xn plus some m minus y. Okay, or I can write xn plus some elements mn minus y or some mn in m. For an arbitrary element I am writing. Okay. Now what xn plus mn, as per the selection y1 we have selected x1 plus some element in, right? Now y1 I have selected x1 plus m1. What y2 I have selected? Somewhere choose x2 plus some element of m. Now here it is xn plus some element of m. What this is actually, is it yn? Can I write this as yn?
Yes, ma'am.
Since yn I can write as xn plus mn for some mn in m. Okay, therefore we get, what we get, this left hand side I'll write again, norm 1 of xn plus m minus y plus m. What can I write on this is it norm of yn? This is yn, na? I am replacing minus y. Right? But we know this converges to 0 as n tends to infinity. Why? We have already proved now. I can call this as number 7. Huh? By 7 I can write this. Right now? But what we have proved? The sequence xn plus m converges to y plus m. Okay? Thus, the sequence xn plus m converges to y plus m in xy m. But what this is a subsequence, right now? Or which is I can write, which is a convergent subsequence of, what is my original sequence? Sn plus m. Okay, therefore whatever the subsequence we have extracted is convergent. Therefore xn plus m converges to y plus m, which is actually a convergent subsequence. Therefore what can I say about Sn plus m?
Convergent.
Converges to which element? Same element, no?
Yes, ma'am.
Thus, this is the Cauchy sequence we have started with, and we have proved it is convergent. Hence, x by m is complete. Complete we have proved, but non-linear space it is already there. Thus, x by m is a x by m with this norm 1 is a Banach space. Yes, any difficulty? If you have, you can ask me now. You must understand this logic, this theme. This theme. Sn plus n is a sequence, Cauchy sequence of elements we have started with, but every element is a set. If it is somewhat difficult for us, right? Therefore, we wanted to extract one convergent subsequence. This is the subsequence we have extracted. Again, this subsequence has every element as a set. Again, to make it simpler, we have extracted one element from every set. Right now. And then we have shown this yn is Cauchy. Once it is Cauchy, it will be convergent because x is complete. Then lastly, our job remains to show xn plus m converges to y plus m, which will imply Sn plus m converges to y plus m. Right now? If you understand this theme, then there is no difficulty to write that. Okay? If you have still any difficulty, you can ask me throughout the proof. Hi, students? Understood the proof or not?
Yes, ma'am.
Yes, ma'am.
Difficulty? Okay.
No, ma'am.
Let us stop then. Thank you for being with me for this lecture.